In the previous section, we introduced parametric curves and did a little bit of algebra and some basic work with parametric curves. In this section, we'll talk about doing calculus with parametric curves. So the first thing we need to do is figure out what the derivative is, or define the derivative or a tangent line to a parametric curve. And that's given by the first box here. If we have a parametric curve C of t with components x of t, comma y of t, where x and y are both differentiable functions of t, then the derivative dy dx, this is the same derivative we've always more or less dealt with, is equal to dy dt over dx dt. So what we're seeing here is you take the derivative of y with respect to t, then you place it over the derivative of x with respect to t. So we'll do an example just to make sure that's absolutely clear. But the next thing we can do is define the second derivative. So we've got a formula below for that, and I'll motivate how this formula comes about after I introduce it. But if we have a function dy dx, or sorry, we have our derivative, well, this is a typo. If we have we're looking for the second derivative, d squared y dx squared, we can find that by taking the derivative of dy dx and plugging in for y in the above formula. So I'll walk through those details in just a moment, but the second derivative of y with respect to x, so this term here is the same type of second derivative we've always dealt with. It'll just be a function of t now. This will also be a function of t, by the way. But it's equal to the derivative of, with respect to t, of dy dx. So that's the derivative that we would have found above here. And then we divide again by dx dt. So where does this come from? Let's think about this as an operator. We've got two derivatives of y with respect to x. That's one way to say this. So two ddx's operating on y. So the outer ddx is this. So the derivative with respect to x. And there's an inner one, ddx of y is dy dx. Okay, well, we know that dy dx, well, we can find that from above here. That would be this expression right here. And dy dx, with a d in front of that, we're really thinking about this as being the differential dt is divided by underneath this d, and it's divided underneath this dx. So we have this ddt over dx dt. So we don't really do algebra with these differentials, but that's kind of what it looks like. So this formula is kind of built on that idea, this sort of look of division that's happening here. Notice that, if it was an algebraic operation, these two highlighted terms would cancel out with each other as a form of one. So it's really the chain rule that's happening here. But at any rate, this is our formula. The second one is a bit more complicated than the first derivative. So you have to keep that in mind if you're looking for the second derivative of one of these parametric functions. So let's see an example of this to be all the more clear with it. So the first thing we're asked to do is find an equation of the line tangent to the curve at the given point. So we've got a curve x equals sine cubed theta, y equals cosine cubed theta, and at theta equals pi over 6, we'd like to find the equation of the line tangent to the curve described by these two equations. Our parameter is theta. And without a given range, we just assume it takes all real numbers, all real values. So theta equals pi over 6 is, of course, in that domain. Now, what we need in order to form the equation of a line is maybe point slope form or slope intercept. I've just written down the equation of a line as our motivation. Ultimately, what we need is the slope of this tangent line for m. So this is going to be found through the first derivative, dy dx, momentarily. And then we need a point x naught, y naught. Well, that point's going to correspond to wherever we are on the curve when theta is equal to pi over 6. So to get the slope first, we note that m is equal to the derivative of y with respect to x. And we use this notation, this vertical bar with theta equals pi over 6. This is quite possibly or quite likely been used in Calc 1 before. So in other words, this says take the derivative of the function, and then for the variable that remains, plug in pi over 6 for that variable, for the variable theta. And of course, x is sine cubed of theta. So its derivative is, well, with respect to theta, we should mark down these pieces of information right here. dx d theta is the denominator here. We're working through what this derivative actually is down below, because once we got to this stage, we realized, oh, there's more work to do here. I'm not just taking a standard derivative. I need to do it for this function and for this function. So the derivative of this function x with respect to theta, again, that's going to be the denominator here. It's 3 sine squared theta, and the chain rule gives us a factor of cosine theta. So 3 sine squared theta, and then chain rule gives us cosine theta as the derivative of sine theta. Okay, similarly, we've got dy d theta, and that comes from y equals cosine cubed theta, and dy d theta is 3 cosine squared theta times the derivative of cosine theta, which is negative sine theta. So again, another chain rule. And when we look at these terms, we've got some cancellations that we can make. We've got cosine squared theta here, cancels with a cosine theta to leave a cosine theta in the numerator. And negative sine theta cancels with a sine squared theta to leave a sine theta in the denominator and a minus sign in our expression overall. So here's our derivative, negative cosine theta over sine theta. That is negative cotangent theta, but we're going to plug in pi over 6, so it's probably easier not to write it that way anyway. So this information is really filling in at this stage. So a little extra work below this main line right here. Now when we plug in pi over 6, we get that cosine pi over 6 is root 3 over 2, sine of pi over 6 is 1/2, and these two of course reduce to square root of 3, and that minus sign just comes along in the expression. So negative root 3 is our slope. So we update that linear equation that we're trying to go for, the equation of the line that we're trying to build. And this is exactly what we've got so far. Now the next question is, what's x naught and y naught? Well, that's the x value and the y value when theta is equal to pi over 6. Again, that just comes from this fact right here on this given piece of information. So in order to find that, we just need to plug in y of pi over 6, or pi over 6 into y, and pi over 6 into x. Now be careful, this is into y and x directly, not dy dx or dx dt or any of those other derivatives. We literally take pi over 6, plug it into sine cubed theta, and we have sine cubed of pi over 6. What comes out of that is root 3, 1/2 to the third power. So let's see the details here. So I see we have a little bit of an error here in our answer. So we've got, just to fill in a line here, or to redo the line, let's fix this with y minus, and if we've got y of pi over 6, again, that's sine cubed of pi over 6, so maybe we'll just fill in an extra step, that doesn't hurt. And then this is minus root 3 times x minus x of pi over 6 is cosine cubed of pi over 6. It doesn't hurt to take this thing a little bit more slowly than what we've done so far. We've got y minus, again, sine of pi over 6 was 1/2, as we saw above. So that's 1/2 cubed. And then this is equal to negative root 3. And this is x minus, this is root 3 over 2 cubed. So this is y minus 1/8 is equal to negative root 3 times x minus square root of 3 cubed is 3 to the 3 halves, or we could write 3 root 3 if we wanted to. Either way is fine, over 8. Now, they don't tell us what form to put this line in. They don't say give us a parametric equation for the line. If they did, a nice trick for that is to just let x be equal to t. So your first component's t, and then whatever y is equal to when you solve for y in this equation, just by adding 1/8, you'll get the rest of that parametric equation. But since they didn't ask for a parametric equation, I'll just give it in terms of point slope form as we have it here. And this is our final answer then. Okay, so there's the slope, or there's the equation of the line that's tangent to this curve at the point pi over, or at the parameter value theta equals pi over 6. The point that that occurs at, let's make a note of that. This is tangent to c of t at the point. This is 3 root 3 over 8, comma 1/8. Okay, so that's the point at which this line is tangent to that curve. Okay, so we can talk about the area of parametric functions enclosed by a region, usually involving one of the axes, x-axis or y-axis. So in the given problem here, we've got that the area A, there's a lot on this page, I'm looking here, A is equal to the integral from A to B, y dx. So this is sort of a generic notation. Y is some function of x, and we integrate with respect to x. And this is to find the area between a given curve, which is y equals f of x, possibly though written parametrically, and the x-axis, right, as we see here, between c of t and the x-axis. So since if we have a curve that's written parametrically, and x is f of t and y is g of t, that makes up our c of t components, then y itself is g of t, as we see written here, and then dx is f prime of t dt, in other words, dx dt dt. Because we really want to look closely at this, we can see that thanks to the chain rule and sort of this, not quite an algebraic elimination, but this is dx dt times dt is essentially dx. And again, this is thanks to the chain rule, not by direct algebra with these things. So that's how this comes about. F prime of t dt replaces dx, and for the reasons I just showed right there. So this becomes this expression right here. Okay, there's another one for area between c of t and the y-axis. That's here. And it's x dy. And our limits of integration are, whatever might be given a to b. We convert this to f of t for x now, and g prime of t dt for dy. Very similar, just a change in the roles of the variables there. So for a curve in the x-axis, for a curve in the y-axis, we've got formulas for each. Notice that the limits of integration do change in each of these. So if this was from a to b, these were x values in this case. And the handwritten formula above, this is for y values, thanks to that being the differential. When we move over to alpha and beta, these are t values, right? The limits of integration will match there'll be variable values for whatever our differential is in that integral. So dt, that means alpha and beta are going to be t values. Okay, so we're asked to find the area enclosed by the curve x equals t squared minus 2t, y equals square root of 2, or t, in the y-axis. So if it's the y-axis, we need to use the formula given above, the handwritten one at the top. So that, again, is just a to b x dy, and then we'll swap in f of t and g prime of t as needed. So we need to figure some things out, though. We need to find the intersection points of this curve with the y-axis. So when we do that, we're setting x equal to 0, which is this function equal to 0. So here we have that equation that results. We solve for t in this. We have 0 and 2. So when t is 0, we should get a y value of, well, square root of 0. and that's 0. And then when t is 2, we'll get a y value of the square root of 2. So that's this upper bit right here. Well, those are y values. I'm sorry, and we don't need y values, we just need t values, right? Because again, we're going to switch to this integral and go from a t value to a t value. So I went a little too far with what I found. These just go straight to here because we're going to plug into this formula. Maybe not quite this formula, we're using the one above that. So it's x dy. So we have here f of t plays the role of x, g prime of t dt plays the role of dy. So f of t is just this function x, and then g prime of t, well, this is y prime of this, or y prime is 1/2 t to the negative 1/2. So there's our g prime of t function right here, 1/2 t to the negative 1/2 dt. So everything's in place for an integration. This is a straightforward antiderivative of the power rule. And what we end up with in the end, simplifying this, is this fractional exponents of 2, and that's about as simplified as we can get this thing. So we'll just leave it as is. Okay, so that's the area between the y-axis and a curve. Again, we could do the x-axis and a curve, but it's all fairly similar. Remember that the limits of integration are in terms of t in these integrals. And to be precise with which function you take the derivative of and which one you do not take the derivative of. If maybe a good rule of thumb is if it's between the y-axis and the curve, then you're going to take the derivative of the y component. X-axis and the curve, it's going to be the derivative of the x component. So for arc length, we've got a very similar scenario. We have a parametric curve given by c equals x of t, y of t, or x is f of t, and y is g of t. Through a quick substitution to our old arc length formula, we can come up with this parametric arc length formula. Again, limits of integration are in terms of t values, and we just take the derivative of x squared plus the derivative of y squared, root of all that, dt. So this is a nice, quick formulaic thing to do. Of course, most of these problems should be trick problems. There's maybe a tricky algebraic substitution or maneuver you have to do to get through it, because they all have to be rigged to work if you're expected to find an exact value here. So in this case, they say find the exact length of the curve c of t given by this expression in x and y for the first and second components over the interval 0 to 4. So that's a t value interval from 0 to 4, and they're asking us to find the arc length of it. Well, it's pretty straightforward. We do x prime squared plus y prime squared, so we need to take the derivative of each of these. We have 4t here, and we have 6t for the other one. So we have 16t squared plus 36t squared, which is really root 52t squared, which is root 52t. And this line here kind of gets us most of the way through this problem. We have 1/2 t squared, evaluated from 0 to 4. And we arrive at 32 root 13 once we take out that factor of 4 from 52, since it's a perfect square. So that's nice and straightforward, not too different from what we've seen in the past for arc length problems. And similar to our Cartesian equations, our Cartesian functions that had arc length formulas, there's also a surface area formula for parametric. So it looks very familiar, right? Remember that this radical component is the arc length component of the surface of one of these solids of revolution, or surfaces of rotation or revolution. And this is that circumference component. So since we're rotating about the x-axis, our distance from the x-axis is y. It could be a function of x. If it's a function of x, we want to use y is just y. It's the distance away from the x-axis. For parametric equations, it's this straightforward. Y is a function of t, and that's 3t squared. So wherever we have this y, we're just going to use 3t squared. Now, for the inner part, it's just like the arc length that we just did. So that should follow pretty well. Alpha to beta is still values of t, and in our given problem, that's 0 to 1. So they asked us to find the exact area of the surface obtained by rotating the curve x equals 3t minus t cubed, y equals 3t squared, t ranges from 0 to 1 about the x-axis. A similar thing would be the case for the y-axis, only this would be an x. So it's pretty straightforward. So things that we'll need, well, we recognize that y is 3t squared, so that takes care of that component. The derivative of x with respect to t, that's 3 minus 3t squared coming from here. Derivative of y with respect to t, that's 6t coming from that equation. And plugging it all into the equation that we have in the box, we have 2 pi, and then y is 3t squared, and then the square root of each of the derivatives squared added together. So there's x prime squared, here's y prime squared. Turns out these two factors will add together, combining like terms here. So we end up with an expression underneath the radical inside this integral that is actually a perfect square. This highlighted term factors into 3 plus 3t squared. If you didn't quite see that, notice that everything in it has a factor of 9, so you can factor 9 away from this polynomial. Since 9 is a perfect square, it could factor out of the radical altogether, and you could have a 3, and then inside the radical will be 1 plus 2t squared plus t to the 4th. Or you just factor it as I've done here. Remember our limits of integration were from 0 to 1. 2 pi times 3t squared, that was 9t squared times 2 pi. So 9 times 2 pi is 18. T squared stays in the integral, of course. So that brings us, catches us up all the way down to here. Now we have a binomial squared and square root of that. So these two things will cancel, and we're just left with 18 pi times the integral from 0 to 1 of t squared times 3 plus 3t squared. This is pretty straightforward. We multiply t squared times each of these two terms, integrate those two terms to get this antiderivative evaluated from 0 to 1, all times 18 pi. When we're done with the details, we should get something that looks like this. So that takes care of all of 9.2 for us. We started with what's the derivative of one of these parametric functions, and we worked all the way to a surface area formula. Now, one thing we didn't see was a second derivative of one of these functions. What I'd suggest is the textbook has at least 1 or 2 examples of that. So have a look. Remember, the formula is, there's a little bit more to it, but in the end, all you're really doing is using this formula. So in other words, you'd find the first derivative via this formula. Then you take that derivative, take its derivative with respect to t, and then divide by dx dt. You can recycle the information in this denominator with the information from that denominator. So that's a nice little shortcut in those problems. Otherwise, we've seen all of 9.2, calculus with parametric curves. So good luck with this one as well.